welcome back. Today's topic is impulse. Let's go ahead and get started. So, impulse is the product of a force and the time over which the force acts. And that quantity, impulse, changes momentum. It's kind of analogous to work in a way. That's a force applied over a distance and it changes the energy of the system. Okay, so there's going to be some parallels. There's also going to be some very huge differences between momentum and work, impulse, momentum, work, energy. Okay, so impulse changes the momentum of a particle or of a system. Again, we are not going to use I. We're not going to use the letter that goes with the word. We're going to use the letter J. And that is because we've run out of I's. We haven't used them yet in mechanics, but it's a very important term in electricity and magnetism. Okay, so that aside, impulse, the symbol is J, is equal to a force times the amount of time that the force is applied. Impulse is a vector quantity, and it's in the direction of the force. Impulse is also equal to the change in momentum. That's the math speak. In the physical world, impulse causes the momentum to change. Okay, so therefore F times T is equal to delta P, or we could even go further. F times T is equal to, okay, so F times T is equal to delta P, which is equal to M delta V. Making the assumption here that mass doesn't change. That's not required. Mass can change, but for most of the problems we're going to deal with, it's going to be the velocity that's changing. Okay, so on the AP side, impulse is the integral of a force over a period of time, and that's because sometimes our forces are changing. Okay, kind of like springs. The impulse that a spring applies to something is going to be a changing force during a period of time. Also, we could draw a little graph and we could have our force and our time, and it would be the area under the curve that would give us our impulse. Okay, let's move on. So the units are newtons times seconds. So force times time, Newton seconds, or kilograms meters per second, which is the same as momentum. Okay, so let's restate Newton's second law in terms of impulse. Well, why do we want to do that? Okay, that's right. It's because Newton actually wrote his second law in terms of momentum, not in terms of acceleration. So how does that work? Well, let's write Newton's second law. F causes a mass to accelerate. Okay, well that's cool. That's cool. So force is equal to mass. Well, what's another way of writing acceleration? What is acceleration? Well, it's the change in velocity during a period of time. Huh, I think we're getting someplace. Now, what if I multiply both sides by delta t? Oh, this is starting to look promising. Force times change in time is equal to mass times change in velocity. Impulse causes momentum to change. Cool. That's really cool. Okay, well, when the forces are changing, we need to say that impulse causes momentum to change. Well, impulse or force is equal to the change in momentum over the change in time, or the change in momentum with respect to time. So this is the calculus world. Okay, so this is how Newton actually wrote the second law. A force causes the momentum of the object to change. Pretty cool. Okay, well, when we think of impulse or impulsive forces, they're generally very large for a very short period of time, like a baseball bat hitting a baseball. Okay, the force is very large. The force of the bat on the ball and the ball on the bat, they're the same, however, anyways. So the force is the same. It happens for a very short time. It happens for the same amount of time on each object. Can't have one object touching the other object for a longer period of time, just like you can't have one object touching the other object harder. That's part of Newton's third law. So we have very large magnitudes over very short periods of time. And you can see that in the graph here. We have a force that goes up suddenly and then comes back down, and the area under this curve would be the impulse. Okay? Well, the impulse of the bat on the ball is equal to the impulse of the ball on the bat. The change of momentum of the bat is equal to the change of momentum of the ball. The force of the bat is the same as the force of the ball on each other. The time is the same for both. What's different? Well, the mass of the bat is different than the mass of the ball, which means that the acceleration of the bat is different than the acceleration of the ball. Okay, that is the thing that's different, is the acceleration. Okay, enough of that. And hopefully you'll be able to use that last little soapbox episode of mine to answer this question. Good luck. See you in a bit. Okay, welcome back. So now we're going to do a little bit of that math stuff. Do a practice problem here. So we're going to have a 1.5 kilogram brick, and it's being dropped on a glass table. I don't recommend you do this at home. We're going to drop it from a height of 20 centimeters. So what is the magnitude and direction of the impulse necessary to stop the brick? Okay, well, let's draw a picture. See if that helps us. Well, here we have our brick. It's going down, and it's going to hit our glass table. So, well, the magnitude and direction of the impulse necessary to stop the brick. Okay, well, let's see what we know about impulse. Well, impulse is equal to force times the period of time. Well, we weren't given anything about forces or times. Well, impulse is also equal to the change in momentum, which is m times delta v. We have a mass, but I don't have the velocity. I can use energy. I can use that energy stuff from the last unit. What kind of energy does the brick have up here when it's first let go? Well, it has potential energy, which is mgh. And what kind of energy is it going to have down here just the instant before it hits the table? Well, it's going to have kinetic energy, 1/2 mv squared. And conservation of energy says that those two things have to be equal to each other. Oh, so that means that mgh is equal to 1/2 mv squared. Masses cancel, meaning that the velocity or the speed of the brick just before it hits is equal to root 2gh, or the square root of 2 times 9.8 times the height of 0.2. Okay, I'm good, but I can't do that one in my head, so let's pull up the handy dandy calculator. Okay, so we have square root times 2 times 9.8 times 0.2. Close that parentheses. And that gives us a speed of 1.97 meters per second. Okay, now what do I need to do? Well, I have the mass. Now I have the final speed. We knew what the initial speed was, didn't we? Okay, so let's calculate what this impulse thing is then. So it's mass times change in velocity. Well, the mass of the brick is 1.5 kilograms. And what's the change in velocity? Well, what's the final velocity of the brick? Well, once the table stops it, the velocity is 0. What's the initial velocity of the brick? Well, before it hit the table, it was going 1.97 meters per second, and it was going down. So the conventional direction up is positive, so down is negative. So negative 1.97. Okay, so that gives us 1.5 times 0 minus a minus a negative 1.97. After plugging that into the calculator, I think it comes out to 2.96 Newton seconds. And the impulse is positive. Isn't that the direction that the table has to apply a force to make the brick stop? Why, yes, it is. Okay, so the impulse, that makes sense. The impulse is up in 2.96 Newton seconds. Okay, well, let's find out what the average force that it exerts on the brick. Well, we have our impulse. Going back to our equations, well, impulse is equal to force times time. Now we've been given the time. We can calculate our force. So force is equal to impulse over time, which is 2.96 over 0.01. Okay, if we're dividing by 100th, it's the same thing as multiplying by 100. So that's 296 newtons of force. Well, what's the average force that the brick exerts on the tabletop? How do I figure that out? Oh, Newton's third law. Well, it says that if the table is applying a force of 296 newtons, then the brick must be applying the same force, but in the opposite direction. Cool. And here's your free response question. Good luck. We'll see you next time.